Hi everyone, welcome to AI Crack channel. This is Akash Bhimwar and today we'll be studying functions lecture 2. In this lecture, we'll be talking about basics of range, types of functions and some problems on domain. So let's begin our lecture with the range of functions, basics of range of functions. And it says range of y equals to fx is the collection of all outputs corresponding to each real number of the domain. So basically the first step is to find out the domain of the function. We have seen that how to find out domain of a function. We have seen the basic rules of finding out the domain. And once we have done that, once we have found out the domain, after that we have to find all the corresponding outputs with respect to those real numbers in the domain. That is the range. That is the basic definition of range. But we are not getting any kind of idea how to calculate the range, right? So let's look at the second point. If domain is a set of only finite numbers of points, then range is the set of corresponding fx values, right? What does this mean? Let's say we have domain as 1, 2, 3, and 4. These 4 points as the domain, basically some finite number of points, right? In that case, we have to calculate the value of function for all these values, that is f of 1, f of 2, f of 3, and f of 4. And those 4 points would comprise the range, right? In this case, only in this case when we have discrete points. Okay, now there can be cases where domain itself is an interval, right? Let's say domain is from 1 to 10, let's say. So we have infinite number of points, infinite number of real numbers between 1 to 10, unless they have specifically mentioned that we have just natural numbers or integers, right? If they haven't mentioned natural numbers or real numbers or integers, in case of real numbers, we'll be having infinite number of points between 1 to 10. In that case, there must be some specific ways in which we can calculate the range of a function. So what do we do over here? We express x in terms of y. From this, find y or for x to be defined or real, or form an equation in terms of x and apply the condition for real roots. What do we mean by that? Let's say we have y equals to, or let's say we have fx equals to x square plus x plus 1. Let's say we have this one. So what do we do over here? We take fx as y and then we express x in terms of y, and we know that x is real because domain is real, and we apply that condition to find out this value, find out the range of this value. Okay, so that is just an example. Now this slide was to give you just an example on how to calculate range of functions. It was not meant to solve problems. We'll be solving more number of problems on range of functions afterwards, once we have done different types of functions and we have mastered calculating domains of functions. After that, we'll be focusing on range of functions. As of now, it was just to give you a basic idea what is range of functions and how do we calculate it fundamentally. Okay. Now let us move forward with different types of functions, and the first one over here is polynomial functions. So if you want to define it formally, then it means if a function f is defined by fx equals to a naught x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus till the end, where n is a non-negative integer and a naught, a1, a2 till an are real numbers and are coefficients obviously, and a naught is not equals to 0. This is most important. Then f is called polynomial function of degree n. So this degree n basically means we have the highest power of x as n. And that's why a naught should not be 0. Let's say if a naught equals to 0, in that case this term doesn't exist. In that case the degree of the polynomial function would be n minus 1, right? If we have degree as n, in that case a naught cannot be 0, right? The important point over here is a polynomial function is always continuous. So what do we mean by that? Since we haven't studied limits and continuity as of now, let me define that in a very crude form. So if I start writing or drawing something and I'm not lifting my pen, in that case the function is called as continuous. Or in a different manner, while drawing a function on a graph, if I'm not lifting my pen, in that case that function is called as continuous function. That is a basic way to define a continuous function, right? Now there are a few examples. We know x square plus we know ax square plus bx plus c as quadratic function. That is also a polynomial function of degree 2. And we know ax plus b. This is a linear function of degree 1. We know ax cube plus bx square plus cx plus d. This is polynomial function or cubic function of degree 3. So these are the various types of polynomial functions over there. Okay. So a polynomial function of degree 1 with no constant term is called as odd linear function. Let's say we have fx equals to just ax. there is no constant term over here. In that case, this function is called as odd linear function, right? Odd linear function. Linear means degree 1 and odd means basically odd degree. Okay. Now moving forward, a polynomial of degree odd has its range minus infinity to infinity, and a polynomial of degree even has a range which is always a subset of R. So what do we mean by that? Let's say we have a function fx equals to ax cube plus bx square plus cx plus d. So this is an odd degree function where degree equals to 3, right? Basically a cubic function. Now if I put x equals to, let's say, minus 10 is per 20 and also x equals to 10 is per 20. These are the two values I'm putting. In this case, this value, this would fetch a power of minus 10 raised power 60, and this would fetch a power of 10 raised power 20. So 10 raised power 40, right? So this is comparably huge in terms of negativity, right? So this is highly negative as compared to this one, right? In terms of magnitude, this is much higher as compared to this one. So basically, if I put minus infinity, x equals to minus infinity, then this entire function would become minus infinity, right? And if I put x equals to plus infinity, in that case, this would definitely go towards plus infinity, right? So range becomes minus infinity to infinity. If you want to talk about the graph of this function, considering that it has three roots, in that case it would look something of this sort. Here going towards negative infinity, here going towards positive infinity. This would look like something of this sort. Now if we talk about a function with an even degree, let's say we have ax4 plus bx cube plus cx square plus dx plus c, basically a biquadratic function. Now in this case, if I put x equals to minus infinity and x equals to infinity, for x equals to minus infinity, this term would overpower and also become positive, right? So basically this entire function would be dominated by this particular term, and it would overpower the entire value of the function. It would also go towards infinity, right? Now if I put x equals to infinity, then this term is infinity, this term is infinity, this two, right? So everything goes to infinity, so that is obvious. Now the function would look like something of this sort. So for negative infinity, it's also going towards infinity. For positive infinity, it's also going towards positive infinity. But over here, we have some limiting value. So basically, a lower cap is there, which is not infinity, which is some finite value. Because for extreme values, it's going towards positive infinity in both the cases. So there should be some finite value over here, which is marking this lower cap over here. So we can say that the range of even degree function is always a subset of R. So it cannot be from minus infinity to infinity. It has to be some finite value till infinity. Right. So this is the kind of range we are going to get for a even degree function. Now talking about algebraic functions, a function f is called an algebraic function if it can be constructed using algebraic operations such as addition, subtraction, multiplication, division, and taking roots, started with polynomials. So basically, the root function is polynomial only. But what we have done different kinds of operations, algebraic operations over there: addition, subtraction, multiplication, division, roots, powers, etc. Right? So this is what we have done over here and form algebraic functions. Now note that all polynomial functions are algebraic, but converse is not true. Why? Because let's say we have two functions, fx equals to x square plus 1 and gx equals to, let's say, 2x cube plus 1. Okay, so these are the two functions, and now we can form a new function hx equals to fx plus gx. So this one is a polynomial function, this one is a polynomial function, and what we have done is we have added. So we have used an operator and also formed a polynomial function. So what we have formed is a polynomial function. So all polynomial functions are algebraic, but converse is not true, right? If we are doing the converse, so let's say we have this function. This is algebraic function, but it's not polynomial. But in case of polynomial, we can form functions with the help of operations, right? So that's why polynomial functions are algebraic, but converse is not true. Now let us talk about rational functions. A rational function is a function of the form y equals to fx equals to gx by hx, where gx and hx are polynomial functions, right? And also hx is not equals to 0. This is the most important point. So basically these functions are also derived from polynomial functions. The important thing over here is the calculation of domain. Let's say we have f1 and f2. These are two functions, and we have defined new function g equals to f1 by f2, right? So domain for f1 is d1, domain for f2 is d2. Now domain for g, that is d, that would be d1 intersection d2 minus all the values where f2 equals to 0. So this is the important catch over here. We have to subtract all the values of f2 where basically all the values where f2 equals to 0, right? d1 intersection d2 minus where f2 equals to 0. So this is the domain for rational functions. Now let's talk about identity function. So basically if we have fx equals to x, basically for all values of x, we have the same value as y. In that case, the function is called as identity function. So this is a special case of odd linear function. We saw that odd linear function is fx equals to ax. In case fx equals to just x, that means the function is identity function, right? We'll talk about this being a bijection afterwards once we have covered the types of functions. Now let us talk about constant functions. And as the name suggests, the value should be constant, right? For all the values. So if we want to represent this in form of arrow diagram, so these are the two sets a to b, and the function is defined from a to b, right? Now we have, let's say, these values a, b, c and d in the domain, and we have just one single value over here, let's say 5. So this is pointing towards 5, this is pointing towards 5, this is pointing towards 5, this is pointing towards 5. Basically that means fa equals to fb equals to fc equals to fd equals to 5. For all values in the domain, it just take one single value, right? In the practicality, that would basically mean fx equals to some constant k. So this value k is constant. If you put any value, any random value which is there in the domain of the function, and for that value, the value would be k only. In graph, it would look like this one. This is, let's say, some positive number 5. K is 5 over here. Okay. So for all x values, the function would be constant, having same value. Now let's solve certain domain related problems for the functions which we have studied until now. So now this one is an algebraic function because we have under root over here, we have plus over here. So it's an algebraic function, right? Let's say this function is f1x, this function is f2x, and this is fx. So this one has domain d1, this one has domain d2. So the final domain would be d1 intersection d2. So let's first find out d1 and d2. Now for D1, we have one consideration. That is, we have under root over here. And what do we mean by that? Basically, that means anything inside the under root should be either positive or equals to 0. So it would turn out to be x square minus 3x plus 2 is greater than equals to 0, right? So if you want to simplify it, it would become x minus 1, x minus 2 greater than equals to 0. If you put it this in the, if you plot this in the number line, we have 1 over here, 2 over here, plus, minus, plus, wavy curve method, right? Now we have to find out all the values which are positive. So this goes over here, this goes over here. We have a filled circle over here because we have the equality as well over here, right? So that basically means d1 is nothing but minus infinity to 1 union 2 to infinity. Now if we talk about d2, in this case we have two considerations. The first consideration is we have under root over here, so everything should be greater than equals to 0. But also this is in the denominator. So that means we shouldn't have equality. So it cannot be 0. All we have is all the values inside this under root should be positive. Okay. That basically means x square minus 3x minus 4 should be greater than 0. That would turn out to be x minus 4 and x plus 1 greater than 0. If you plot that in the number line, we'll have minus 1 and we have 4 over here. But we have, since we have just the inequality over here, not the equality, we'll have open circles over here. So plus minus plus. So this goes towards here, this goes towards here, right? Now in this case, d2 would be minus infinity to minus 1 union 4 to infinity. Now if we have to take the intersection of d1 and d2, let's plot the number line once again. So we have minus 1, we have 1, we have 2 and we have 4. So we are going here, we are going here, we are going here and we are going here. So the common region is this one and over here is this one. So eventually d1 intersection d2 would come out to be d2 only. So that would become Let's write it over here. B equals to minus infinity to minus 1 union 4 to infinity. Right. So this is the final domain for this function. Now let's talk about this question. Find the domain of the function fx equals to this plus this. So we have two functions, f1x equals to this and f2x equals to this. Again, we have two functions over here. So we have to find out d1, we have to find out d2, and we have to do d1 intersection d2, right? So for the first function, we have fx equals to 2 upon x square minus 4. So that's pretty simple. It can take all the values except where denominator becomes 0. So x square minus 4 should not be 0. So basically x square should not be equals to 4. X should not be equals to minus 2 and 2. So these are the two values which are not acceptable in domain. So x basically d1 becomes are basically all values minus 2 and 2. Okay, now if we talk about this one, so here we have x cube minus x should always be greater than 0, right? Because anything inside log should be positive. That basically becomes x square minus 1, or we can directly write it as x minus 1 x plus 1 greater than 0. Now we have number line over here. So this is 1, sorry, this is minus 1, this is 0, and this is 1. Plus minus, right? So we have to find out the positive zones. So open circle over here, open circles, these values, yeah, these two values. So basically for d2 we have minus 1 to 0 union 1 to infinity, right? Now we have to take the intersection of both d1 and d2. So intersection would mean d2 only, but only we have to subtract these values. So d2 minus 2 to minus 2 and 2, right? So this would be our final domain. Now I'll give this question as the homework question, but let's discuss the few considerations in this question. So the first consideration is the entire function should be greater than equals to 0 because it is inside the under root, right? So we have log 1 by 2 5x minus x square by 4 should be equals to 0 or positive, right? Now when we remove log from here, 5x minus x squared divided by 4 should be less than equals to 1. Why? Because we have a fraction over here. If we have some value which is more than 1 over here, in that case that would become negative, right? Because we have a fraction base over here, right? So we have to do the reverse inequality. Also, the basic condition of any log is 5x minus x squared divided by 4 should be positive. So these are the two conditions which we have to follow to solve the domain of this particular problem. So we have to keep in mind this inequality sign that actually changes when this fraction is over here, right? So this lecture was till here only, and in the next lecture we'll be talking about more number of functions and solving more number of domain problems or maybe range problems. So let's meet in the next lecture. Thanks for watching.